All right, welcome back, my scientists. Okay. So we, just as a quick refresher, talked briefly about electrons or waves and how we can calculate the wavelength, the frequency, the energy. Okay, and all that's going to be very important here as we come in and we discuss our model of the atom. Right. So far we've basically just said that atoms, I'll draw a quick little picture here, right? We have our center, right, the nucleus where the protons and neutrons hang out, right? And then around that, right, we have the electron cloud where the electrons are, okay? But how exactly did we get there, right? So kind of brief history, it was originally thought that atoms were just like hard little spheres, kind of like bowling balls, but very, very tiny, or marbles, if you will. Okay, but again, very, very tiny. Right? And over time, they discovered, okay, they're made up of protons. Oh, there's also electrons in there, right? And there's these things called neutrons, right? And eventually, it got turned into this model that we have here, where we know that there's a nucleus that's very dense in the center, right? And there's very much empty space here in this electron cloud, right? And electrons are hanging out there. Okay, so how do we get there, right? How do we know where the electrons are? Okay, and that brings us to this guy called Niels Bohr, right? Niels Bohr, he was really fascinated by these lamps that some scientists were using, right? And what they were doing was they would take basically a glass tube, right, like we have here, right? And they'd fill it up with a gas, right? In this case, hydrogen, right? And they'd pass some electricity through it, and they got the hydrogen atoms all excited, and they'd start glowing, right? And they'd glow this kind of purplish light, okay? And what they found out was that if that light goes through a prism, it will split up. You know how like a prism, if I go back to a couple pages here, a prism will split white light up into the rainbow, okay? For hydrogen, what they were finding was that when it splits up, instead of getting the full rainbow, they only got 4 distinct lines. And the thing is, it was always those 4 lines, and only those 4 lines. And if I did a different element, I would get different lines. Right? So if I flip over to the next page, right, here's some other examples. Okay, so we got hydrogen up here at the top. That's the same one we we're just looking at. I got mercury here and neon. Okay, and these are what we call line spectra. Okay, and these are unique to each element. Right? They're kind of like a fingerprint. Okay, so basically we use them to help us identify elements. Right? In fact, this is how helium was first identified, because helium was actually not discovered on Earth. It was discovered on the sun. Right? And the way they did that is they pointed one of these devices at the sun, and they saw that they got a different set of lines from any other element that they knew of at that time. Right? And they said, well, if it's got these unique lines, right, then we must have a unique element. Okay? And so they discovered it, and they call it helium after Helios, the Greek god of the sun. Okay, so Niels Bohr, he was wanting to use these spectra to try and wanted to figure out like why do we have these lines? Right? Why are they where they are? Why are they always the same color? Why are they always in the same places? So he developed this model of the atom where instead of just having electrons kind of flying around outside around that nucleus, they are in what we call energy levels, right? So if I look at this one here on the left, okay, I got my black spot in the middle, there's my nucleus, and I've got these rings on the outside. Okay, and these rings, I'm just going to label them 1, 2, 3, 4. Okay, these rings are what we call energy levels. All right, we got that over here, energy levels. Okay, and these energy levels, these are places where the electrons can be. Okay, so I can have an electron that hangs out here, or here, or here, or here. Okay, but I can't have an electron hanging out here because it's in between energy levels. Doesn't happen. Okay, they can only exist in these very distinct spots. Okay, so that's the first part that Bohr says. Okay, so now how does this get us to this line spectrum? All right, well, let's focus on just one electron here. I'm going to put an electron over here in energy level 1. Okay, if this is where the electron normally hangs out, right, and just so we're clear, electrons can hang out in level 2, 3, 4, right, depending on how many electrons we have. Okay, but this is just our only electron, so it always hangs out closest to the nucleus. It's going to hang out in level 1. Okay, this is what we call the ground state. Right, wherever the electron normally resides is the ground state. Okay, now, if you've ever gone babysitting, right, one of the major rules of babysitting is you never give the kid sugar, right? No soda, no cake, no candy, okay? Because that sugar is going to get the kid all amped up, right? They're going to get really excited. They're going to be bouncing around, going around all over the place, and it's going to be a mess. Okay? Same thing happens with electrons. Okay? If I'm going to use a little squiggly line here. Okay, if I give some energy to this electron, okay, what that electron can do now is it absorbs that energy, just like the kid absorbs energy when they eat all that sugar, and it can jump up to a higher level, okay? But it has to have enough energy to get up to that level, right? If I only have enough energy to get right here, I can't jump up to level 2, right? And that's not going to work. Okay, I'm going to give that electron enough energy to get all the way up to here, right? Or maybe enough to get all the way up to here, or maybe enough to get all the way up to here. Okay, so this first step here, this is what we call absorption. Okay, it's going to absorb that energy. Okay, and when it does, it's going to get excited and it's going to jump up to a new level. Okay, so let's say it goes all the way up here, and I'm going to put a little star next to the E, right? This shows us that it's in the excited state. Okay, just like a little kid gets excited when he gets a lot of sugar, right? This electron has a lot of energy, so it's getting really excited. Okay, now, just like if you give that kid sugar, like 20, 30 minutes later, eventually that kid's going to crash, right? It's going to have that sugar crash. All that energy is going to suddenly disappear. Electrons are the same way, okay? They go up to that excited state, but they can't stay up in that excited state. Instead, what happens is that electron is going to fall back down, okay? So if it falls down, it can go down, excuse me, to the next level, right? Or it could go down to the next level after that, or all the way back down to the ground state. Okay? When it does that, each time it's going to release some energy. Okay? So, step 2 is called emission. Okay? So that's where those lights are coming from, right? The electron absorbs energy, jumps up to an excited state, right? Can't stay there for very long, and so then it falls back down, and when it does, it releases that extra energy as light. Okay, so that tells us where the light's coming from. So where do we get the specific colors from now? Well, that's about those energy levels. Okay? The further away from the nucleus you are, the more energy that electron needs to have, right? So that's why when we absorb energy, the electron goes away from the nucleus. Okay? When it falls back down, it releases some energy, right? Now, how far it falls down determines how much energy it releases. Okay? If I have my electron, and let's say that electron falls all the way down from level 4 to level 1, right? So this is a 4 to 1 transition. It's releasing a lot of energy. All right, go back to our discussion about energy and color. All right, a couple of pages ago, we flip back up to here. Where is it? There it is. Okay, we said that violet light, right, that's the shortest wavelength, right, and because it has the shortest wavelength, it's going to have the highest energy. Okay, short wavelength, high energy. Okay, so coming back down here, I'm dropping a lot, I'm releasing a lot of energy. Okay, so this is going to be the most energy that could be released here. All right, so this is going to be something closer to blue or violet light. Right, big drop, closer to violet. Okay, if instead I drop only part way. Okay, let's say I do this transition from 4, but I only go down to 2. Okay, I'm still dropping a decent amount of energy, but not as much as my 4 to 1. Okay, so I'm releasing less energy. Okay, so I'm going to be somewhere in between in my colors. Okay, so this one's going to be closer to green light. Okay, because it's a smaller transition, less energy. Finally, if I only drop from 4 to 3, okay, I'm only releasing a small amount of energy. Okay, and so, my light that's being released is going to have a little bit of energy. Okay, so the lowest amount of energy that's in the visible spectrum is going to be red. Okay, so big drops mean you're closer to violet. Small drops mean you're closer to red, right? And you can get to somewhere in between, right? Whether you say it's yellow or green or blue, right? That's going to be kind of a judgment call. Okay, but biggest drop should be violet. Smallest drop should be red. Okay, so a couple of things here. All right, again, we've got our ground state where it normally hangs out. Okay, the electron absorbs energy, right? That's number 1. Okay, it goes up to that excited state, hangs out for a little bit, but can't stay for very long, and then it's going to undergo emission. It's going to drop back down to a lower level, and when it does, it releases that energy as light. Okay, and then the color of the light is determined by how far it drops down. It's a small drop, it's closer to red. If it's a big drop, it's going to be closer to violet. Okay? Now, let's flip on over here. There's a few questions just to kind of help summarize things. I would say, pause, read through this section here, in this section, and then try answering these questions. And then we'll go through the questions together here real quick. Okay, so let's take a look at these questions. All right. How do we know that electrons are only at specific energy levels in an atom? All right. We can say because of the line spectra. Okay, so there's only certain lines for each element. Okay, and those lines, they correspond to electrons moving in the atoms. Okay, different atoms are going to have different spacing between their levels. Okay? And so there's going to be different spaces between, and then when the electrons drop back down, they're going to release different amounts of energy, giving us different colors of light. Okay, and if you go back up and take a look, you can see some of them have very few, some have a lot. Okay, so it all depends on what the element is, how close those levels are. Okay, which energy level has a higher amount of potential energy, second level or the third energy level? Well, we said the further away from the nucleus you are, the higher the energy is going to be. Okay, so it always goes 1, 2, 3, right? 1 being closest, so the third energy level is going to be the highest energy. Okay, number 3, will an electron moving from 5 to 1 release more energy than an electron moving from 2 to 1? Well, we just saw, looking at our example here, 4 to 1, right? That we only went up to 4, but we can apply here to 5 to 1 as well. Okay, the bigger the drop, the more energy it's being released. So 4 to 1 versus 2 to 1, or 5 to 1 versus 2 to 1, the bigger drop, right, that's going to be releasing more energy. So I'm just going to say bigger drop. Okay, number 4, will the electron moving from the 5th to the 1st energy level release an energy wavelength closer to red or to violet? Well, just like what we were saying before, the bigger the drop, the closer it is to violet. Okay, so 5 to 1 is a large drop, right? That's going to be closest to violet. All right, flip on over to the next page. When an electron absorbs enough energy to move up at least one energy level, it gains this is from the reading part, this is a quantum. All right, quantum of energy, that's just the smallest amount of energy that can be transferred, right? It's like a little packet of energy. I can't, give off any smaller amount than 1 quantum of energy. Okay, number 6. When atoms absorb energy, electrons move into higher energy levels, right? That's our step 1. Right? These electrons lose energy by emitting light. That's step 2. The emission of light can be passed through a prism, and one can see the diffraction gradient, these frequencies of light emitted by an element separate into discrete lines, which is called an atom's, we didn't use emission, right, but emission line spectrum. Okay, every element has its own unique amount of electrons and energy level spacing because each element has its own emission line spectrum. Okay, number 7. When an electron in an atom is at its lowest possible energy level, it is said to be at its ground state, the state where an atom is not absorbing a large amount of energy. When an atom absorbs energy in the form of electricity and sometimes fire, which we'll do in the lab, the electrons of that atom are excited, and the electrons are sometimes considered to be in an excited state. How about that? Okay, and I'm going to pause there where I'm not going to talk about number 9. I guess we're going straight to 11. I'm not going to talk about those ones just yet. We're going to come back. We'll talk about those ones next time.